Mastering calculus starts with treating the subject as a logical machine built one part at a time. A 4-question checklist decodes how these parts fit together, replacing the need for rote memorization. We begin with a baseline capability. For a simple string of terms, like y equals 3x to the 5th plus 4x cubed, the process is straightforward. You differentiate each piece separately by bringing the power down to multiply and reducing the exponent by 1. That rule gives us 15x to the 4th plus 12x squared. But the logic shifts when those distinct terms are smashed together into a single complex unit. Basic arithmetic intuition often fails when systems combine. Analyzing this type of complex change requires a structured mental model to keep the components organized. Many students attempt to differentiate x squared and sine of x separately, and then multiply the results. This approach produces an incorrect answer because it ignores how the two functions interact. Look at this expanding rectangle. When the length and the width grow simultaneously, the total area increases for two distinct compounding reasons. You have to account for the growth of the length against the width and the width against the length. We capture this interaction using the product rule. In our joined function, the first term stays exactly as it is, multiplied by the change in the second. Then we add the second term, multiplied by the change in the first. Applying that pattern to our terms, x squared stays while sine becomes cosine. We add sine of x while x squared becomes 2x. The product rule proves that in any interconnected system, change is driven by mutual interaction rather than isolated behavior. The second checklist question asks, are two things divided? When variables are stacked, the division introduces a rigid subtraction sequence into the formula. For this stacked equation, we use the quotient rule. To keep the framework stable, lock in the foundation first. Take whatever is on the bottom and square it. Now we build the numerator. Take the bottom exactly as it is, multiplied by the derivative of the top. Then subtract the top, multiplied by the derivative of the bottom. Pay close attention to that minus sign. Because subtraction is not commutative, reversing this sequence will completely invert your result. Since we are dividing by the square of the denominator, its growth rapidly diminishes the total value. In calculus, this means the growth of a denominator acts as a brake, suppressing the overall rate of the system. The final checklist question is often the most important. Is something inside something else? Nested functions must be processed sequentially, working strictly from the outside in. Imagine this nested function as two distinct machines. There is a large outer shell, a power of 5, and sitting inside of it is a smaller machine containing 3x plus 1. First, differentiate only the outer machine. Bring the 5 down and reduce the power to 4. While you do this, the inner machine remains perfectly static. Second, extract the derivative of the inner machine. The derivative of 3x plus 1 is 3. We multiply that against the entire outer structure to reach the final result, 15 times the quantity 3x plus 1 to the 4th. Test this framework on the equation y equals e to the x squared. Pause the video now, identify the layers, and solve it. The outer machine is the exponential function, which remains unchanged. The inner machine is x squared. After differentiating the outer shell, we multiply by the inner derivative, 2x, giving us 2x e to the x squared. The chain rule reveals how deep hidden layers of a system ripple outward to multiply the total rate of change. Calculating these complex derivatives allows engineers and scientists to find the exact stationary points of dynamic systems. This curve represents a physical scenario. The climbing line, its instantaneous slope. When the rate of change reaches exactly 0, the system hits its limit. At the peak, the tangent line snaps horizontally. This threshold, where y prime equals 0, identifies the maximum or minimum. Analyzing the architecture of a problem using these questions identifies the specific points where change stabilizes or reverses. This 4-step mental model is your checklist. First, what is the object? Second, are pieces multiplied? Third, are they divided? Fourth, is one inside another? Running any equation through this sequence provides a consistent framework to analyze and map the mechanics of any changing system.